So the Cramer-Castillon problem, which was proposed by Swiss mathematician Gabriel Cramer and solved by the Italian mathematician Jean de Castillon, was solved in 1776. And what is this problem about? The problem has to do with if you're given a circle, this green circle here, 3 points on the plane A, B, and C, you want to find triangles inscribed in the circle whose sides pass through each one of A, B, and C. And it turns out there's only two solutions for this problem. There's only two triangles that satisfy these conditions, so they're shown here for the particular choice of A, B, C. Here's one triangle, this gray triangle. You can notice here that this side does pass through A, and this other brown side here does pass through B. And the third side passes through C, which in this case is internal to the circle, but it doesn't have to be. And here's a second triangle, and you always get these two solutions because this problem ends up being translated into the language of fractional linear transformations and matrix multiplication. In the end, you get a quadratic equation, and there are two solutions to this quadratic equation, and you get these two triangles. Okay. Now, I want to show you guys a few experiments I've been doing with this and how it relates to Poncelet families. So let's go to my mathematical notebook here. And first of all, I just want to show you guys what this thing looks like dynamically. So I can move these 3 points around, and I can look at the two solutions here, and I'm solving this thing behind the scenes using these fractional linear transformations and the quadratic algorithm that is out there to solve this problem. And P2 doesn't have to be inside, it can be outside. In fact, I can have both P1, P3, 2 points inside, right? And you can get solutions. Sometimes you cannot get solutions depending on where these points are, but that's not germane here. You can also do the same thing, since everything is projective, for an ellipse, right? So you can ask the same Cramer-Castillon question, which is given 3 points on the plane, P1, P2, P3, on Wikipedia they're A, B, C. What are two triangles inscribed in a given ellipse whose sides pass through these points? And you get the same exact math. You can basically just use affine transformations, and you're going to get the same kind of dynamic of stuff, right? You can get the same stuff and blah, 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 and move P1, P2, P3. In this case here, I think I can move P3 like that, so forth and so on. Okay, now, yeah, you can also extend this, and the math generalizes for any number of points that you can place around a circle or an ellipse. In this example here, I'm showing n equals 5, so I can actually, just array n points outside of a circle or an ellipse, and I can ask the question, okay, what are n-gons that have this Cramer-Castillon problem property? And they said basically here two pentagons, a green one, an orange one and a magenta one. And you can notice if you actually work it out, you're going to see that each one of the sides of each individual solution is going to pass through the 5 points specified. Okay, so this is Cramer-Castillon. I'm going to leave a link in the description for a chapter of a book about geometry that explains how the algorithm to solve this. Okay, so the topic on this video, or the properties that I want to talk about in this video, they come from a mathematical musing, which is the following. I want Cramer-Castillon to meet Jean-Victor Poncelet in the following sense. I'm going to let these 3 points here, okay, these 3 points, these three P1, P2, 3 points, not be just placed manually anywhere on the plane, but I want them to be controlled by a family. In this case, I'm going to use a Poncelet family of triangles, and I'm going to let P1, P2, P3 be determined by the position of vertices of a Poncelet family. So let's look at a Poncelet family here. For example, I'm picking, one of the simplest families. It's basically a family of blue triangles, okay, inscribed in a first ellipse, an outer conic, and circumscribing an interior circle, which is concentric with a conic. So the caustic of this family happens to be this brown circle over here. And how am I going to play this game? I want Cramer-Castillon to be controlled by it. So I'm going to use the caustic itself. In this case, it's a circle, but it could be an ellipse, to be the Cramer-Castillon circle. So I want to ask the following question. Given the 3 vertices of this Poncelet family, 1, 2, 3, and I can move this family around, okay, What are solutions to the Cramer-Castillon problem using the caustic as the circle? Okay, let me turn off a few more things so I can better explain this. So is this clear? I'm just trying to combine these two seemingly disparate worlds. Um, I think Poncelet came a little bit later, Cramer-Castillon. I'm not sure if he thought about this combination, but it's an interesting combination, and you do get some interesting results. A first result is the following. The Simedian point of both triangles, solutions to the Cramer-Castillon problem controlled by the specific Poncelet family, are shared. So if I move this family around, the Simedian point of these two triangles is shared. Is it always shared? Like, are the incenters shared? For example, so let's actually exaggerate the aspect ratio of the outer ellipse, and you'll see here that the incenters are not shared, okay, of these two triangles. Are the body centers, the centroids of each triangle, shared? No, they're not shared. How about the circumcenters? Well, by definition, the circumcenters are going to be shared because both of these triangles are inscribed in the same circle, the caustic of my Poncelet family. Okay, how about the orthocenters? Are they shared? Let's decrease the aspect ratio of my outer family. Here's my outer family. No, the orthocenters are not shared. How about the centers of the 9-point circles? Also not shared. How about the Simedian points? Somehow, magically, the Simedian points are shared, and they are shared dynamically. So I'm going to go ahead and loop this family around so you guys can see this. So it's quite surprising that using this construction, the Simedians of these two triangles that know nothing about Poncelet are shared. Now the next question you can ask is, since they're shared, what is a common locus they trace, right? So I can actually say, okay, show me the locus. And as it turns out, the two loci are the same curve, and they are ellipses. So this object here, this orange curve that you see here, I'm numerically reporting that this is an ellipse and this is the major semi-axis length. So when this thing shows up here, it's basically saying, okay, I've numerically detected using least squares that the locus of x6 is an ellipse. Here's its minor axis, here's its major axis, here's its minor axis, and here is its aspect ratio. Is this aspect ratio similar to the aspect ratio? Is this ellipse similar to this outer ellipse here? I don't believe it is. Do I have a way to check that? Actually, it is. Okay. No, it's not. Okay, so this one is, yeah. So this ellipse here, they don't have the exact same aspect ratio, although they're close. So for example, this one is 1.33 and this one is 1.30. So the aspect ratio of my Poncelet family is not identical. It's close to the aspect ratio of this Simedian locus. So other things that you learn here is that there's a special there's a special object called the Brocard Circle. Let's go ahead and draw that. So the Brocard Circle of a triangle has as its diameter the line connecting x6 to the circumcenter. Okay, so since the circumcenter is shared and the Simedian point is shared, the Brocard Circle of these two Cramer-Castillon triangles is going to be shared. Is there a radius constant over the family? No, this is not the case. We'll see this in a minute. How about the Brocard axis? The Brocard axis connects x6 to the circumcenter x3. So the Brocard axis of these two triangles, Cramer-Castillon triangles, is going to be shared. As you can see here, and let me make this go a little faster by decreasing the sampling. You can see here that the radius of the circle cannot remain constant since the distance from x6 to the center of the system is varying. X6 is riding on an ellipse, so the radius of the circle is going to vary. But the cool thing is that both of these triangles share the same circle, the same Brocard circle. Okay, how about another object known as the, well, actually a pair of objects known as the Brocard point, or the Brocard points of each one of these triangles. Turns out they're also shared, right? They have to be on the same circle, so the Brocard points lie on the Brocard circle, but it turns out that they actually shared. So you're seeing there the shared Brocard points of these two triangles that were generated using this Poncelet construction. Is this always the case? Like if I use a different Poncelet family, and I'll show you guys in a minute, you're not going to get the same phenomenon here. It's very special to this particular family. There's actually two families that accomplish this feat. Now, let's see, what is another question I can ask? Okay, the Brocard points are shared, and they are the foci of a well-known object connected to Brocard geometry known as a Brocard in ellipse. So let's go ahead and show the Brocard in ellipses, and let's actually make this system a bit more eccentric. Okay, may turn off the locus of x6 for now so that I can clean this up a bit. So interestingly, and let me exaggerate even more, the eccentricity of my outer Poncelet ellipse. The outer Poncelet ellipse is this black thing. Imagine it's actually going sideways and closing out. I can show you guys how this thing is closing down by scaling this whole system down. It's a pretty eccentric outer Poncelet ellipse, and I'm making it so I can exaggerate the eccentricity of this common Brocard in ellipse. So the Brocard in ellipse of a triangle is tangent internally to all the sides, to the three sides. It has the Brocard points as their foci, and I think this is sufficient to define it. Okay. Now it turns out that the Brocard in ellipse of both triangles is shared. So you can see here, is this Brocard in ellipse, does it have stationary aspect ratio? I'm actually showing here that they're both the same. There's two Brocard in ellipses being drawn on top of it, one on top of the other, but they're not stationary. They don't have a stationary aspect ratio. So you can actually think of instantaneously at each one of these pairs of Cramer-Castillon solutions as two triangles belonging to the same Brocard porism. And what does this Brocard porism look like? It has this caustic here of the Poncelet family as its circumcircle, and it has this instantaneous Brocard in ellipse as the common caustic. So these two triangles here, the orange and the magenta, they belong to the same porism, except that I'm not drawing the one-dimensional family of triangles that would belong to this porism. These two triangles are just two elements of that porism. And as soon as you move the Poncelet family around, you change the porism, because the aspect ratio of the caustic of the Brocard in ellipse is changing. So instantaneously, the two Cramer-Castillon solutions are members or elements of the same porism, but across the Poncelet family, the porism is actually changing. Okay, now let's look at what happens to this, and let's bring our aspect ratio a bit closer, closer to 1, so this thing is not so eccentric. Okay, now let's look at what's happening. By the way, I'm not gonna go into this, but the locus of my Brocard points is not an ellipse. Okay, the locus of their midpoint, actually the locus of the center of my Brocard in ellipse is an ellipse, but the locus of the Brocard points themselves, or the foci, are not ellipses. But I want to show you guys what happens if I change my family to another family, a well-known family, a Poncelet family, the confocal family. Okay, so you get a much messier picture. So this blue triangle here is a three-periodic in an elliptic billiard. Okay, and the billiard is this black ellipse here, and here's a confocal caustic. Now when you do this, you can see that this completely disorganizes everything. Okay, I no longer share Brocard circles, so let's stop that so we can look at them. Here's one Brocard circle, here's another Brocard circle, and I no longer share Brocard points or Brocard in ellipses. You can see that the Brocard in ellipses are drawn here in this aquamarine color, and they're not shared. So this kind of harmony that we saw with the in-circle family is not happening here. In fact, there's almost no harmonies that I've been able to detect if the controlling family is the confocal family. So let's go ahead and animate that, and you can see that This is totally disorganized. If I just switch back to what we had before, the Incircle family, everything gets organized. So magically, in the Incircle family, all these Brocard objects magically coalesce into single objects. How about if I went to the homothetic family? What do I get? I also don't organize anything. I have distinct Brocard in ellipses. I have distinct Brocard circles. I have distinct Brocard axes, etc., etc., etc. So we're not getting a lot of harmony here. Of course, there's a lot of interesting remarks that can be made about the loci of various centers in the homothetic pair. But we're not going to spend time talking about this here. How about the Circumcircle family? What is a family with? What is a Circumcircle family? It's a Poncelet family. These blue triangles inscribed in a circle and circumscribing a concentric ellipse. You don't get any a priori visible harmonies here. These objects are all over the place. Okay. Now let's show you guys another family where you get a lot of harmony, which is a bicentric family. Let's go ahead and scale this down a bit. And what is a bicentric family, first of all? Let's go ahead and make a quick refresher, also known as the poristic family. This is a family of triangles inscribed in a circle and circumscribing a non-concentric circle, this brown circle over here. So I have a family of triangles, like so, with these properties. It just turns out that this family emulates or reproduces a lot of the phenomena, the sort of harmonious phenomena we saw with the Incircle Poncelet family. Namely, and you can see this already, the Brocard in ellipse is a varying in ellipse, but it's shared. The Brocard circle is a varying circle, and it's shared. You can see here that the Brocard circle is always going through the center of this bicentric caustic, which is the center of the circle where both Cramer-Castillon triangles are inscribed. So the x3 of the Cramer-Castillon triangles is over here, and therefore the Brocard circle is always going to pass through this. But since x6 is also shared, and since the locus of x6 in this case has an additional property, it is actually a circle. So in the encircle case, the locus of x6 was an ellipse. In this case, you get an additional phenomenon whereby the locus of x6, and how do I know this is a circle? Because I'm numerically showing that this thing was detected as an ellipse and that its aspect ratio is 1. So you get the circularity thing. So you're getting shared Brocard in ellipse, shared Brocard points, shared symmedian point, shared by definition a circumcenter, and a circular locus of the symmedian point. Now let's look at a final example before we part, and that is the example where the controlling family is actually the Brocard porism. Since we're getting a lot of these Brocard phenomena, let's now, and let's recap what the Brocard porism is. Let's actually put it on the right side, and let's turn a lot of these guys off so we can actually first of all remember what the Brocard porism is. So the Brocard porism, which arose, right, as the pairs of Cramer-Castillon triangles controlled by either the Encircle Poncelet family or the Bicentric or Poristic family. Now I'm using the Brocard porism itself, a proper one, to control Cramer-Castillon. So look at the, here's a triangle of Brocard porism. What does this thing do? This is a family of triangles inscribed in a circle, blue triangles, circumscribing a very special in ellipse known as the Brocard in ellipse. And the two, not shown here, the two Brocard points of this family are stationary at the foci of the in ellipse. So now I'm saying, okay, if I let the Brocard porism triangles be P1, P2, P3, or ABC in the Wikipedia notation, of my Cramer-Castillon problem. And the Cramer-Castillon problem now is going to be looking for two triangles inscribed in this elliptic caustic. Are there cool properties for the two solutions? And when you start turning on the objects, for example, first thing, let's turn on the Brocard points of these two Cramer-Castillon solutions. They're not shared. How about their Brocard axes? Am I drawing both here? Oh, okay. This is obvious. Let's see here. Let's see if there's some. Oh yeah, there it is. Yeah, they're not shared. Yeah, I wasn't a particular uh, aspect ratio here of my Brocard porism that one of the Brocard circles was too small. But you can see here that as I iterate through the porism, there's two distinct Brocard circles and two distinct Brocard axes. Okay, they're not shared. How about the locus of, let's say, the incenters? Are they shared? Okay, so here's where you might be getting some, let's see here, some additional properties. Yeah, so this was curious, right? So let's see here. So like, can I scale this down further? Or can I scale this up further? Let's go ahead and scale this to 8. Yes. So it could be the case that the two incenters are sharing the same locus. As you can see here, this locus is clearly not an ellipse. How about x2? Hard to tell if they're being shared or not. Let's go ahead and double that size. It looks like this locus is being shared, but also non-elliptic. How do I know it's non-elliptic? I can actually light up the label and let the program tell me, oh yes, so the locus of x2 seems to be an ellipse, and they are the same. How about let's go back to x1. x1 is not an ellipse, so the locus of x2 is an ellipse in the Brocard case, which is an interesting result. How about x3? x3 is also this ellipse here, and they're the same. How about x4? Orthocenter, also an ellipse, so we're getting plenty of elliptic loci here, which was not the case if you go back to, and I didn't go over this, but to the encircle object. We'll go back there and we'll show you guys that this is not the case there. How about x5? Also an ellipse, and I'm just looking at here, that I'm looking at this area here, and I can see here that x5 is an ellipse as well. They're shared, except that the two x5s are not shared instantaneously. They lie at different locations of this ellipse. They're out of phase. Okay. How about x6? Also shared, but not in the same location. Let's go ahead and make this be 12. You can see that there's one x6 here, and there's another x6 there. Okay, so as I scroll through these families, and one of the Brocard circles is probably pretty small. If I change the aspect ratio of this family, I can make the other Brocard circle appear more clearly. Yeah, there it is. So you can see here the two x6s, they are not shared, but they are riding on the same elliptic locus. Let me go back really quick to the encircle case so we can compare what was happening then. Okay, let's move the scale down a bit, and I just want to show you guys one added phenomenon that differentiates the encircle case from the Brocard controlled Cramer-Castillon. We were talking about before about the locus of the fact that x6 was shared and that its locus was an ellipse. How about the incenter? The incenter loci are not shared, or the incenters are not shared, and their loci is not an ellipse. Nor are the loci of the barycenters, which are not shared. The circumcenters, by definition, fall on a point. Nor are the loci of the orthocenters, nor are the loci of the centers of the Euler circles. How about in the case of the bicentric pair, which we were looking at before? And let's now go ahead and try to position these guys in a way that we can all look at it. So let's make this bicentric family be less bicentric, right? Like that. And now we can recall that this is the family interscribed between two circles. And let's just quickly go over what's happening. We saw that the locus of x6 in this family was a circle, right? So you can see it here in the middle. Here's a circle. The aspect ratios of the shared shared side-median points are circles. Their aspect ratios are 1. How about x5? Not only are they not shared, they're not circles. They're not conics. How about x4? Not shared, not conics. x3 by definition at the center. x2 not shared, not conics. x1 not shared, not conics. So what's really amazing about the Brocard is that you lose the organization in terms of, so the two Brocard circles are distinct, the two Brocard axes are distinct. You got 4 distinct Brocard points, but you got something interesting regarding loci. So loci of x1, I'm not getting any ellipses here, but loci of x2 are shared ellipses, are common ellipses. Let's go ahead and go back to that scene. You can see that it's this thing here, and let's make this guy be a bit more eccentric so I can better look at the locus of, I guess I have to do x16, right? So here's the loci of the x2s, which are not shared, but the interesting thing here is that they ride the same ellipse. And we have not seen this in the other cases. How about x3? The two x3s, this family, is not inscribed in a circle, so the two x3s are going to occupy different locations. Here's one x3, and here's another x3. So if I jog this family a little bit, let's jog this so we can see the x3s moving. So the x3s are moving. They're not in the same location, but they're sweeping the same ellipse. So when you control Cramer-Castillon with Brocard, with the Brocard family, you get this new set of phenomena. How about x4? Again, they are not shared, but they sweep the same ellipses. So I'm displaying here that these are the same ellipses. How about x5? Same phenomenon. Sweep the same ellipses. Here's one x5, here's another x5. How about x6? x6, not a circle as it was with the bicentric pair. Not shared as it was with the encircle and bicentric pair. Here's one x6, and here's another x6. They, both of them share. They're not shared, but they sweep the same elliptic locus. And you can keep going for higher points in the encyclopedia of triangle centers, x7, x8, x9, and you can end up finding out many more properties. But I guess this is what I wanted to share with you guys. The highlights being when Cramer-Castillon is controlled by the Circumcircle family. So you get this kind of a situation. What if I do 1? Yes. So here's a situation where Cramer-Castillon is controlled by the Circumcircle family. You get, most importantly, the sharing of x6, right? And you get the elliptic locus of x6, and you get these two triangles belong to the same instantaneous Brocard porism. Then you have another set of results concerning the bicentric pair, and you also get a shared x6. You get shared Brocardine ellipses as in the encircle case, and now x6 is going to be describing a circular locus. And then finally, when the family is controlled by a Brocard porism, and this one is too exaggerated, let's make it be less eccentric by bringing this guy here, then you get a new set of phenomena, and you get that several of these triangle centers are no longer shared, but they're now riding the same elliptic locus, even though they're not shared. So all of these facts are new as far as we know. They result from this combination of these two disparate worlds, Cramer-Castillon and family of Poncelet triangles. And we're just discovering them experimentally, and we're welcoming any input or contributions here, ideas, questions. Thanks for watching, and I'll see you on the next video.